interest includes geometric learning with a particular focus on thinking graph architecture that exploits symmetries, equivariance in data. His other areas of research include causal discovery, graph network, as uncertainty estimation. The title of Francesco's talk today is see graph neural network. Floor is yours.
Hi everyone. So yeah, I'm Francesco. I work at GSK. Actually, I work in the artificial intelligence group, which is a group. It's about 100 engineers and researchers right now. And I am an AI fellow. So in principle, I am doing like a postdoc. I'm a researcher inside the company. And what we do in practice is to work at the bridge between machine learning, AI, and let's say biology and drug discovery. The program is still open, so I know there are open roles for this fellowship program. It's like a postdoc, so if anyone is interested, please feel free to apply. And today I'll be talking about symmetries in machine learning and especially in graph neural networks. I know we have already talked about that today, but yeah, I'll try to say something more. Does it work? Since it's not moving. Okay. So when talking about symmetries, we know that they exist in nature. They are crucial in how we perceive and also interact with the world. And in principle, they are simply transformations that leave certain properties of an object unchanged or invariant or even equivariant. It depends on what we are interested in. So for example, if we look at this image, it's a tree, that's clear. But if we look at also these images, they are still tree. So we know that, but in general, without the notion of symmetry, we wouldn't be able to perceive these things. So we will perceive them as different entities, while being, let's say, symmetry aware allows us to be much more data efficient, because a single image, so let's say only this one, is enough for us to understand what is the number 3, what is the graphical representation of a tree, and so all of them contain the same amount of information. So in machine learning, we know that in principle we can learn symmetries. So if we have, let's say, a bunch of images like all the trees we have seen before, and we train a classifier to learn to classify a tree from another digit, it can learn them. So in principle, if we present a model with an exhaustive data set, so let's say all the possible rotations and translation of the same image, we can learn symmetries. But in general, we can also do something better, because if we want, we can directly embed them in a neural architecture. So there are some famous examples. So for example, recurrent architectures exploits the time warping symmetry. Convolutional net, seems I'm not lucky today with this thing. Okay, convolutional network can allow us to exploit translation in data. Transformers, we have seen them today, are actually permutation invariant, and also graph neural network are permutation invariant. So what this allows us to do is to have a better inductive bias and an improved data efficiency. So we need much less data to learn and solve the same task. As we've seen before, there are results from earlier this year from Bruna, which has shown how much less data we need in order to solve the same task. So we have this thing. So this one contains the same amount of information of this whole a lot here. So the question I'll try to answer today is whether we can embed other symmetries in a particular architecture that is the graph neural network, in addition to the permutation one. So I'll touch on that again in a bit. So the mathematical framework that we use to study symmetries is group theory. So we have talked about that a lot today, so I think I can simply skip it. So I will talk about equivariance and invariance in principle. So if I give you an example in the group of n-dimensional rotation and orthogonal matrices with matrix multiplication. Equivariance means that if I first apply a rotation and then another map, it's the same of applying first the map and then the orthogonal transformation. While invariance means that if I apply a function to a certain input x, or I apply the same function to a transformation of the same input, it results in the same thing. So about the graph neural network. So before starting with that, how many of you are familiar with graph neural networks, or at least have ever heard of them? Okay. Okay. So in principle, we have a graph structured data. So instead of using, I don't know, classical data or grids as we use with images, now we have graph structured data. And we have a graph, we have a bunch of nodes, and each node is associated with a certain feature, V. We have features associated also with edges, and we possibly have graph level attributes, which we call U. So this is how a graph network block operates. Here are also the formulas. So in principle, I start with a graph with a certain set of features and embeddings for the nodes, edges, and global quantities. And I updated them through these operations here, and I obtain a new graph with updated quantities. And here you see that I update my edge attributes by applying a sort of parametric function. In general, is a simple MLP through to the concatenation of the old values of the edge attributes and the node attributes to the source and target node of the edge and the global attribute. And I do the same also for the nodes, where I use the previous value of the node attribute plus a permutation invariant aggregation of all the edges that are incoming to this node. And same thing for the global attribute. So the key thing here is that these raw functions, which are aggregation function, they must be permutation invariant in order for the graph network to be permutation invariant. And they can be like, I don't know, element-wise summation, mean, max, or something like that. So in order to add other symmetries on top of the permutation invariant, we need to understand our data better, because in general, it doesn't make sense to apply this reasoning. So to exploit symmetries if we don't know what we are dealing with. So we can start by thinking to the fact that node features may have different meanings. So, and they may obey different symmetries in general. And so we may want to treat some of them explicitly. So here I will consider the case where node features are the concatenation of two things. So the first one, I will call it X. They will be the coordinates of the nodes in the graph, and H will be the remaining set of features. So in principle, what I'm doing is to embed a graph in a Euclidean space. Or, I mean, I'm talking about the Euclidean because it's easy to visualize, but in general, we can think about something else. So, but they will be coordinates. So each graph can be associated with different coordinate embeddings. So here you see that these two are the same graphs. The values of H, E, and U are the same. So the node embeddings, the edge embeddings, and the global embeddings are the same. I have changed only the coordinates. So they are the same thing embedded in two different ways. Okay, so now I will try to use this thing that I have done. So decoupling the spatial geometry of the graph from everything else in order to try to build some equivariance or invariance to some symmetries. So to do that, I want to define this function here. So I'm defining what I call a relative distance preserving map. So basically it means that if I start with two graphs, which are the embeddings of the same graph in two different coordinate sets, such that this property is satisfied. So I have two graphs, I embed them in two different ways in terms of coordinates, but they satisfy the fact that the relative distance between neighboring nodes in the graph is the same. Okay, so in principle, I can have an initial graph and rotate it, will satisfy this thing. And then if I apply this function phi to both the graph, what I obtain are two updated graphs in which this property is still satisfied. So neighboring nodes still have the same distances. So let's try to visualize it. So I have this graph here, And I have another transform. I have embedded the same graph in another way. So clearly this property is satisfied. A simple example of a map satisfying this property is the identity function. So clearly the two new graphs satisfy it. I can add a translation, or I can do even something else. I can rotate it, so I can apply a Euclidean transformation in general, or whatever. I can even do something that is not rigid. So I haven't the picture, I haven't done it here, but in principle, if I start with this graph here, which is like a square, even if I stretch it, let's say like this is not a Euclidean transformation, but it still satisfies this property. So even this one is a transformation that is allowed in this case. I can also do something else, so in principle. And two things to note here is that Euclidean transformations that we have seen satisfy this property. And the second thing to note is that this function here, this relative distance preserving map, in general can be equivalent to some transformations. So for example, this choice here is equivalent to Euclidean transformations, while if I use this other choice here, it is not equivalent to Euclidean transformations. It's really easy to prove because you will have two Qs, so some terms will not cancel out, so you cannot say it. So okay, this is the proof. It's really simple. So to show that this thing is equivalent to Euclidean transformations. Okay, so now we can extend the notion of graph neural network to exploit the fact that we have decoupled the coordinates of the nodes from everything else. So we have this different graph architecture in which we are treating the node coordinates in a different way, and we are also updating the edges in a different way. So we are considering only the relative distance here, and yeah, that's the architecture. And it's really similar to the one we have seen before, except for that. And by construction, it can easily be seen that the updated values of the edges, H and also U, they are invariant to different coordinate embeddings. For example, they are invariant to Euclidean transformations of the coordinates. And the coordinates themselves can be updated in an invariant, but also in an equivariant way. Everything depends on how you define this function phi. So with the one I've shown you before, you can prove that you can update them in an equivariant way if you want. So in principle, with this architecture, you can be invariant to, for example, Euclidean transformation or every relative distance preserving transformation. So, okay, that's cool. Let's see if we can do even something more, because here with Euclidean transformations or with this thing here, we can do something quite nice. But maybe we want to be invariant to scale transformations or to other non-orthogonal transformations, let's say. So the thing is, maybe we can consider angles now. Since we have the notion of coordinates, we can also compute the angles in the graph and see what we can do. So for each node which has two edges, we can define the angle. And so we can define this relative angle preserving map now. So if we start with two graphs in which only angles are preserved, distances don't need to be preserved anymore, and I apply this function phi, this is a relative angle preserving map if the two updated graphs still satisfy this property. So now relative angles are preserved, not distances, so only angles. So as an example here, if I start with this cube, a transformation can be this one. So here I have preserved every angles. So they are all 90 degrees in principle. So the property is satisfied. And then I can apply a function phi, which is a relative distance preserving map. So the easiest one is again the identity, or the one we've seen before, or I can apply a rotation or a translation or whatever. And so all of those will be relative angle preserving map. So now the nice thing is that we can allow for conformal transformation of the embeddings, and these include also Euclidean ones. So again, with this thing in mind, we can now extend even more the architecture we have. And we can define this angle preserving graph block, where we have, in addition to edges, nodes, coordinates, and global quantities, we also have angles. So each angle in principle can be associated with a certain feature set. And we have that by construction, the angles, the edges, the nodes, features, and the global features are invariant to different coordinate embeddings, provided that the angles are preserved. So for example, we have invariance to conformal and Euclidean transformations, while X, so the coordinates again can be updated both in an invariant and in an equivariant way. Everything depends on how you define your map to update the X size. So we have these two architectures. I think we have already talked about how they compare with each other. So on one side, we have this distance graph preserving block in which we allow for Euclidean transformations, but also non-rigid transformations like these ones, while for the angular preserving, we allows for everything that preserve angles. So we can stretch, we can delete, we can do more complex transformations, let's say. So another thing is that they are not only invariant or equivariant to global transformations, since what matters are only the relative distances or relative angles. We can show that we can be invariant or equivariant even to local transformations. So for a nice example is the one of molecular conformations. So if I have a molecule and which is composed of two subgraphs connected by a bond, I can rotate one of the two subgraphs and be equivariant to the equivariant or invariant to this transformation. So if I see a molecule in a certain conformation, and then I see the same one in another conformation, both this conformation will result in the same, let's say, information propagated through the network, because the network will be invariant to these types of transformations. It can be useful or not. And yeah, the other thing is that these two architectures, if you want, you can combine them. So you can try to preserve both angles and distances. And in this case, you will allow only for rigid Euclidean transformations in which local transformations will be no more allowed. Yeah, there are other results. So we can show that these two architectures that I have presented can be seen as generalization of other known architectures that have been shown to be state-of-the-art in some examples. Okay, now I want to show a couple of experiments which I think are quite nice to see what to expect from this type of architecture and what to not expect. So the task here is quite simple. So I want to classify 3D polytopes. Okay, so they are defined as graphs. They are represented as graphs where the xi are simply the coordinates of the vertices. So my data set will be like this. So I have a training data set where I have a single polytope a single sample per polytope. So during training, while I train my neural network, the network is seeing only one polytope. Sorry, only one sample per polytope. So it's seeing a cube, an orthoplex, an icosahedron, and so on. While at test time, I want to test the network on random transformations of the same polytopes. Okay, so at test time, in principle, I have 5 elements. At training time, I have 5 elements. At test time, I will have 500 elements, and they will be random transformations of the one in the training set. So if I start with only orthogonal transformations, so the cube will be simply rotated and moved, what I have is that the architectures that we have presented, they have a perfect accuracy at test set, while a standard graph network is not able to solve the problem. While at training time, obviously, all of them can solve the problem. So, okay, we know that, we were expecting that because we have seen that the architectures are invariant to Euclidean transformations. So that's okay. So what if now I add also dilations in addition to orthogonal transformations? So my cube now can be also stretched. Now I have that only the network that is able to deal with angles can have a perfect accuracy at test time, while the other two really struggles. And again, this is something expected. Now I want to see, okay, what if I make the problem even more challenging? Now I will add non-orthogonal transformations. And by non-orthogonal, I mean that I can stretch the polytopes in whatever way I want, like that, whatever, it can happen, whatever. So what would you expect? I would have expected that all the networks would have failed on this task. But actually, what we have seen is that if we apply non-orthogonal transformations with different amounts of non-orthogonality, we see that the network that is dealing with distances will fail, okay? The standard graph network is failing, that's okay, we know that. The weird thing is that the network that is dealing with angles is not failing, so it's perfect even at test time with non-orthogonal transformations. We thought a bit about it. Actually, the explanation should be pretty easy. Since you have angles and you can deal with them, in principle, what it has done is to learn to distinguish polytopes based on the sum of the internal angles, which is preserved thanks to the Graham-Miller theorem, even for higher dimensional polytopes. So, but this is something that is not expected, let's say. So, last question is, how many training samples does a GNN need to generalize well? So if we don't build these symmetries, these invariants to symmetries in our architecture, and we want to learn them, how many data do we need to learn them? Actually, quite a lot. So for example, even for orthogonal transformations, while this invariant architecture needs only one sample at training time, a standard graph network, since it has to learn these types of symmetries in the data, it will need up to 100 samples at training time, for non-orthogonal even more. So in general, you need, this means that if you don't build the symmetries in the architecture, you need a lot of data to learn something. While if you build them in the network themselves, you can solve the problem in an easier way, in a more efficient way. But again, it depends on what you want to solve. Yeah, this is another problem. QM9, you may be familiar with it. In principle, is a data set of molecules for which you want to predict some quantum chemical properties. And here we have shown that not only these types of architectures are better in terms of accuracy, let's say, or in this case, this is the mean absolute error, but they also converge faster because they need less data. So you can solve the problem and reach a really good solution in much less time, and because you're using less data in principle. Okay, so now to the question someone was talking also about before. What happens if the symmetries we are expecting in the data are not there? So we have built architectures that are invariant to some symmetries. What if we apply them in the wrong context? So for example, we can apply these architectures to a digit classification problem, to an image classification problem, or to the travel salesman problem. Notice that the MNIST and CIFAR10 here are the graph version. So I'm not dealing with images, I'm dealing with graphs. So here, clearly, there are not the symmetries we are expecting, because maybe it's not trivial to see. So, you know, in MNIST, if I rotate a digit, it's still the same digits, right? The problem is that when you translate it into a graph, you are embedding not only the foreground, so the image, but also the background in the graph itself. So if you rotate an image, only some pixels of the image are rotating, while the foreground remains fixed. So in principle, you are not applying an orthogonal transformation, let's say. So yeah, this results in non-trivial transformations that are not, we cannot address with these architectures. And in fact, what you see is that a standard graph network on this task is better than ours, because this means that we are not looking at the right types of data sets for these architectures. So we can use them, they are really powerful, but on the right data sets. They are, let's say, computationally efficient. So you are only doing something more, but they are really computationally efficient. So they are really similar to the standard graph network in general, unless you have a very dense graph. So if you have a really dense graph, like in the travel salesman problem, where you start with an almost complete graph, here the network that has to deal with angles as a computational overhead, which is significant, because when you have a complete graph, you have n square edges, but the angles are in the order of n cube. So this doesn't scale well. Yeah, again, it depends on the type of data set that you're using. Yeah, just some final remarks now. So as I've shown, the nice thing that I want to point out is that with this type of architectures, you can deal not only with global symmetries, but also with local ones if you want. And sometimes it can be useful. There are data sets or tasks in which it is really useful to exploit the equivariance in the coordinates. Like, for example, if you want to simulate an n-body dynamical system, it's really important to be equivariant to the initial set of coordinates, let's say, because if you start from another set of coordinates, which is a Euclidean transformation of the initial one, the behavior will be exactly the same. It will only start from a different initial position, but the whole rest of the behavior will be exactly the same. In general, you can apply the same reasoning to other quantities other than coordinates. So I've done coordinates because it's easier to visualize. You can think about something else. And yeah, an open question, it may be interesting, is whether by using the same type of reasoning, you can build invariance or equivariance to other groups in addition to the ones I've shown there. Yeah, if you want more details, everything I've shown is in this paper. We will update an updated version with some of the pictures and the result I've shown here today. But yeah, that's all. If you have any questions.
Oh, I just wanted to ask about the TSP application. Yeah. So is this Euclidean TSP first? So
yeah.
And so what's actually the performance of this compared to other more traditional methods?
So I know that graph networks, when applied to the travel salesman problem, are nearly state of the art because they are really fast. So if you want to compute the exact solution for an unknown problem, they can extrapolate quite well. The task you want to solve here is, okay, you start with a complete graph. The downstream task is, okay, you want to infer which of the edges of this complete graph are those that are present in the optimal path. So it's an edge classification problem.
Is it a supervised method?
Yeah, it's a supervised.
So
yeah. You need a training data set. Yeah. Yep.
Can I ask a kind of stupid question, which is I didn't really follow how the architecture worked. Could you maybe repeat that and remind me how exactly like the input data fits into the graph? Because it seemed like we're doing some sort of iteration on the like values of the nodes, and how does that relate?
Yeah, so you start with so your data is a graph, okay, in which each node has as a vector in terms of features. So like, suppose that you have an image in a standard computer vision problem, then you can think about it as a grid in terms of a graph where you have features only on the nodes, which are the pixels, but you have no features on the edges, okay? So the edges are simply connecting the pixels. So when you deal with graph networks, you can add something on top of that. So in addition to having features on the nodes, you can also have features on the edges, and you can also have features for the whole graph itself. So the way in which a graph network works is to update the values of each features. So each node, edge, coordinate in this case, or global features, by taking by computing a nonlinear function of neighboring nodes, usually. Okay, so you compute a nonlinear function of neighboring nodes or incoming edges for the nodes, and something like that. And once you do that, you do this using this sort of computational graph here. You obtain a new graph in which you have new values for all the attributes. So you have new values for the edges, new values for the nodes, new values for the global attribute, and so on. And what you hope is to learn a better representation of the graph that can lead to let's say, a representation of your data that is easier to deal with in order to solve the problem that you want to solve. You can think about it as a generalization of convolutional neural networks in principle, where the data is not agreed, the input data is not agreed, but it's a general graph.
Okay, and so in a classification context, like.
So in a classification context, it depends on the problem you want to solve. Since you have nodes, edges, global quantities, it depends on what you want to solve. So for example, on the example I've shown with molecules, in which you wanted to predict some quantum chemical properties of molecules, what you were doing was to do a regression on the global quantity, where the global quantity was the property that you was trying to predict. For example, in TSP, you are doing a classification on the edges, okay? So in principle, you are sort of attaching an additional layer at the end of your stack of graph layers, in which you will pick every edge and try to classify it. Or you can do the same with nodes. So I don't know, in social networks, you may want to, I don't know, predict communities. You can do that by trying to classify nodes, and you can do that by attaching an additional head, which is trying to predict the class associated with each feature of the node.
Okay, great, thank you.
Okay. Thank you.